for another go at classical mechanics, eh, Jono?
Nah, it's first attempt, Kev. Never sat the course last year, eh?
Really? I'm sure I saw you in some of the videos, didn't I?
Yeah, you did indeed, but that's because my idiot brother Jonah sat the course. He managed to land the initial gig providing edutainment for online lectures somehow. I don't know. You know what university hiring practices are like. Anyway, you'll see him at some point with his stupid cat in the hat and Top Gun sunglasses clown show.
Yeah, I remember that, Dross. Didn't last long.
Nah, it didn't last long at all. Barely saw out the pilot. 57 takes, and that was the best they got. His acting's about as good as Ben Affleck in Batman. And his problem solving? It's worse than his acting. So he ended up failing that course so hard. Anyway, when I caught wind that he was getting dropped like some fat beats from that role, I was in like a shot to snaffle up. Been in the gig ever since.
Definitely made more of a go of it than Jonah, that's for sure.
Hell yeah. Fortune favours the brave, Kev. You've got to grab your opportunities with both hands and work hard. If I can pull out the sort of magic I did in Quantum, I'll be dead set on for a uni medal. Might even hang it off this chain here. Be so rag. Totally Flavor Flav, if you know what I mean.
Welcome to PHYS2113 Classical Mechanics and Special Relativity for 2022. This is a short video introduction to the course, and what I want to go through is who's teaching it, a quick overview of what's in the course, how I'm going to teach my half of the course, what the assessment looks like, what the lab component looks like, and a couple of minor details. More complete details of everything I'm going to talk about here will be either in the course outline, which will be on the Moodle site for the course, or elsewhere on the Moodle site for the course. Okay, so who's teaching the course? Given that I'm on this video, it's probably me. For those of you who don't know me, my name is Adam Mikulich. Many of you will have had me for PHYS2111 Quantum Mechanics in T1. For those of you who have, welcome back. For those of you who haven't, nice to meet you. I'm going to be teaching the first half of the course. The second half of the course is going to be taught by Oleg Tretyakov, who you'll run into later in the term. Quick overview of what's in the course. The name for the course, Classical Mechanics and Special Relativity, suggests that both of those topics are going to be in there, which they indeed are. But there's actually kind of three topics in this course because there's a little thing that joins the two in the middle. So the first half of the course is going to be, as suggested, classical mechanics. It's going to last for about 3 weeks. What you learn in first year mechanics is how to attack mechanical problems, you know, projectiles, objects sliding, rotating objects, with Newtonian methods where you're basically using balances of forces and Newton's second law, force equals mass times acceleration, to understand and predict the dynamics of various things. What are the forces? What are the accelerations? What are the velocities? So forth. What you hopefully learn in first year is that you can solve a whole pile of problems like this, but as the problems get more and more difficult, you end up having more and more struggle to solve the problems. You have to introduce forces like normal forces and so forth. And sometimes the maths gets rather difficult to solve. Where we want to go at the start of this course is to introduce some more advanced methods that enable you to solve the more difficult problems that you start to see in mechanics. There's going to be two techniques you're going to learn. They're both advancements on Newton's original method. One is called the Lagrangian method. The other one is called the Hamiltonian method. Both of them are somewhat more mathematical than the Newtonian approach, and you sort of need to understand the method for how to implement them, which we'll teach you in the course. And they sort of fit together as almost like a nice little pair. Once you get far enough past them that you've sort of done both, you can sort of see the similarities and the differences between them. And one of the interesting things that you start to learn is that in addition to the Newtonian approach that you learn in first year, you kind of have this nice toolkit for attacking problems where you can look at the problem and decide, oh, I want to use the Newtonian approach or the Lagrangian approach or the Hamiltonian approach, and then solve that problem. And depending on the problem, one of these three will probably be the stronger or easier one to use, and sort of selecting which one to use and then working out how to deploy it is actually a skill that you really want to practice. And we'll spend a lot of the first 3 weeks doing exactly that. Once we get to week 4, we're going to make a small topic change. I'm going to go back to the topic of oscillators. In first year, you will have done simple harmonic oscillators, so just an oscillating object, mass on a spring, pendulum, that sort of thing. What we're going to introduce is oscillators that are subjected either to a damping force, so something that tries to prevent the motion, or what's known as forcing, like a force that tries to drive the motion. And we'll also look at systems where both of those things happen. There's a damping and a forcing, and there you can get some rather interesting behaviors like resonance turn up. That'll be the end of my half of the course. Oleg will take over at that point. He will stay on oscillators, but what you're going to do is look at coupled oscillators. So what happens if you have 2 oscillators joined together? What happens if you have 3? What happens if you go to the limit where you've got, you know, a million objects all connected by springs, which is really useful because it starts to look like, you know, a crystalline solid where you've got atoms connected by bonds. He'll look at some techniques for solving those sorts of problems, normal modes, that sort of thing. And the idea behind that is to set you up for courses that you'll see in third year, like solid state physics, where you have phenomena that rely on sort of coupled oscillators. Phonons in solids is a good example for that. He's also then going to make a topic change, and the last 3 weeks of Oleg's part of the course is going to be on special relativity. Some of you will have done that in higher Physics 1B special. Some of you won't. Doesn't matter whether you have done it or you haven't done it. He's going to start out with a short introduction to special relativity on the basics. So for those of you who've done a little bit before, it'll be a revision. For those of you who haven't, there'll be your introduction to the course. And then he's going to work up to a stopping point, which will basically be introducing 4-vector notation. And the reason why we like to stop there is that when you get into higher years, you will build on that 4-vector notation in order to do other pieces of physics. So to give you one example, there's a course in third year called electrodynamics, where you basically look at electromagnetism in the relativistic limit. And there you want to have that mathematical framework of 4 vectors so you can move fairly quickly to building an understanding of what's going on in that case. There's other subjects like particle physics and general relativity where that same special relativity sort of formalism is really important to understand. Okay, so you'll learn that in this course. That sort of gives you an overview of everything that's in the course. Looking at how it's going to be taught, I'm going to speak about how I will teach my half of the course. I'll let Oleg talk in more specifics about how he's going to run as we approach him taking over in week 5. My half of the course, for those of you who've done PHYS2113 quantum mechanics in a previous term, I'm going to run very similar format to that previous course. So it'll be sort of quite familiar to you. If you're new to it, the way I'm going to run the course is focus all my lectures into the earlier part of the week, and then focus on some more active learning approaches very late in the week. So in each week, there will be somewhere in the vicinity of 2 to 3 hours worth of video lectures available. They will be on YouTube and linked to in the Moodle site. You can watch them in your own time. So you're free to fix your timetable however you like. If I think through my past students, some of them have just binge watched the entire week in one go. Some of them have cut them up into half an hour a day so that they can sort of digest the subject. Some have pieced them wherever they can fit them. It's up to you how you want to get through that material. The important thing is that you get through that material by the Thursday of the week. On the Thursday evening, there's going to be a weekly quiz and a weekly problem set due. I'll talk about that a little bit more when I get to the assessment. And those 2 tasks that are due basically help us design the Friday sessions, which is where your active classes, where ideally you turn up to campus, or at least you have a scheduled time if you're doing it online, are going to be. So the classes on the Friday, there'll be 2 of them. We've tried to manipulate the timetable a little bit so that this works. There'll be a tutorial class that's going to be from 10 to 11. It will be in Old Main Building room 230. So it's one of the physics building theatres on the top floor. There'll be a 1 hour break in between where you can get lunch. Might be a little bit early for some of you, but I can't really shift the timetable further down to fix that. And then there'll be a workshop class that will run from 12 to 2 o'clock. That will be in the Tyree building, which is the one right on the front of campus where the light rail from Kensington back to the city goes. It will be in room G16 of that building, which is a flat reconfigurable room. And I want a flat reconfigurable room for the way that I'm going to design that workshop class for this course. And I'll talk about that in a moment. So the tutorial session in the mornings will be given by Ian Torvaldsen, be very similar to the tutorials for 2111. So the focus will be on looking at the weekly problem and possibly inspired a little bit by some of what comes out of the weekly quizzes as well, to try and delve into, sort of understanding that weekly problem and getting to grips with some of the more difficult aspects of that particular problem. The workshop class, what I'm going to do is start out by looking at the quiz. There'll be a smaller number of quiz questions for this course, and I'll explain why that is in a moment. And then I want to focus on problems for the rest of the course. So let me just preface the design of that workshop course as far as this course is concerned. PHYS2111 for quantum mechanics. One of the difficulties with that subject is understanding the concepts of the science. And one of the easier parts of it is actually the mathematics. In a sense, if you think about quantum mechanics, what you're really doing is just first year linear algebra and then trying to make sense of how to use first year linear algebra to understand this very new sort of physics of quantum mechanical systems. And so in the workshop classes for that, we often spend a lot more time on quiz problems designed to sort of test and push conceptual understanding and on explaining, how the maths fits to the physics and how we understand the way the world works. Mechanics is quite a different subject. In terms of concepts, it's very simple. You've got, a body sliding on a surface or sliding down a slope. You've got a projectile flying through the air. You might have some object that's rotating or a mass hanging on a pulley. These are all really simple. The concept's not very difficult. There's forces and there's motion. What gets difficult is the mathematics, because now often what you're dealing with is trying to solve first, second order differential equations, and you need some fairly specialized approaches and techniques to do that. Because of that shift from something that's more conceptual to something that's a bit more problem solving, this is why I sort of changed the workshop classes for this particular course. There's a smaller number of quiz problems. There's usually only 4, maybe 5, focused at just making sure that we're pinning down some of the key aspects of the various techniques we're using. That usually takes 20 minutes, maybe half an hour. And then the remaining 1.5 hours of that workshop class, what I'm going to do is do some separate mechanical problems. Some of them will be exam-like, some of them will be more tutorial-like. And the way we're going to do them is we're going to be in a flat classroom that's reconfigurable, break up into groups. I'm going to give you a chance to work through the problem yourselves so that you can get a little bit of experience at actually taking a new problem, breaking it down into the steps to get to the point where you solve it. And then we'll work through those one by one with the aim of leaving that workshop class having done a few problems in any particular week with a particular technique. So we might start out with Lagrangians, work our way through to Hamiltonians, and get some real experience applying it to actual problems so that when you get to the final exam, which will have that style of problem in it, you'll have plenty of experience at actually applying the techniques. The workshop class is going to be available online. I'm going to try and do it as a hybrid class. Because I'm not in the physics building, I'm not going to have my nice super duper hybrid setup that I had for PHYS2111 because it's too hard to take it halfway across campus and back. So I'm going to be running with a slightly lighter version of this year. It's going to be new, so we may have to debug it a little bit, but hopefully it works okay. But when it comes to this class, because of that nature of working in groups in problems, it's probably significantly better if you can come to campus to make the effort to come to campus. But I will make it available hybrid online if you can't make it to campus, so you can still participate in that class. Okay, so that's how I'm going to teach my half of the course. I'll basically do that as 4-week sets. working my way through the various topics that we'll do in each particular week. The assessment for the course is going to have 3 components. There will be a problems and quizzes component, which will be 20%. There will be a lab component, which will be 20%, and I'll talk about that at the end. And then there'll be a final exam, which will be worth 60% for the course. There won't be a midterm exam for this course. I've gone a little bit cold on the idea of midterm exams in the 3+ system for 2 reasons. One is that if you're having a midterm exam in a term that's basically 8 weeks long, we're giving you an exam after 4 weeks, and that's not very long in terms of understanding physics to actually think about that material. And so I always feel not so good doing, what is essentially a summative assessment. Do you know this or not? At a point where you haven't had very long to consider it, okay? The other reason why I've sort of gone a bit cold on midterm exams is that in the midterm exam, you examine the first half of the course, and then in the final exam, you have half of the exam on the first half of the course. And so in the end, what you end up doing is examining the first half of the course twice and the second half of the course once, and it's never really made sense to me why you would do that. So I find the better way, particularly for the compressed terms, is just to have the summative assessment at the end, which is the final exam. That's the point where I work out whether you actually learned anything, and then have the assessment that's during the term, which is the problem and quizzes, designed more from a formative perspective of giving you an opportunity to learn how to do the problems in an environment where it's okay to make mistakes. So that problems and quizzes component of 20% will be divided 10% each between my half and Oleg's half. I'll let Oleg tell you how he's going to use his half when he gets closer to teaching his half of the course, but my half will be, the 10% will be evenly split between the problem and the quiz for each of the weeks. So that'd be 2.5% a week, divided by the two tasks is 1.25% each. The way I mark it is not necessarily on accuracy, it's on ability to demonstrate engagement with the material. What I mean by that is that it's okay to get it wrong. I actually want to provide you with an environment where you can make mistakes and it doesn't cost you marks, because often if you are able to make mistakes, then you're learning things from your mistakes. The whole point of this course is let's attack problems and find out where we go wrong and then learn from that, okay? That does mean that I will be looking for you to engage properly with the materials. So if you think that I don't mark it and I don't check it, you're in for a surprise. I do have a close look at what's going on. If it looks like you've just randomly guessed the multiple choice, and I'm very good at spotting when you have, if someone just puts up a half-hearted attempt or a blank page for the problems, don't expect to get the marks. I want to see that you've actually given it a red hot shot. But if you give it a red hot shot and it's not right, that's perfectly okay, because sometimes you have to get it wrong in order to get it right later. And the place where I want you to get it right is where it counts, which is the final exam, okay? So that's 10% of the assessment there, and it'll have a small task each week. The quiz normally takes 10, maybe 15 minutes at the most to do, depending on how much you want to think about the individual questions. The problem set for each week is basically designed off a past exam problem or exam style problem. So everyone says they want experience doing exam problems. That's exactly what you'll get here. They're designed to be done, in an exam type time frame. So 20 minutes, maybe 30 minutes to do. And you shouldn't spend a huge amount of time on them, right? There's small amount of marks, the small amount of assessment. The key thing is that you have a bash at it and make sure you get some experience at just getting the entry to problems, because usually once you've got that entry to problems, solving the rest of it is not the hardest part of the whole thing. Final exam will be at the end of the term. It'll be an online exam split 50-50 between Oleg's half of the course and my half of the course. And I'll talk a little bit more about that when we get later into the term for that. The lab component of the course will be 20%. And what we're going to do this term is continue a trial that we had in last year's course, which unfortunately got a little bit affected by the lockdown that happened after week 4. So we want to trial the redesign of the labs that we did last year, this year, hopefully without getting an interruption. And it's a bit of a redesign that goes from an old system of doing labs where you would do 2 or 3 labs across the term. and you would do them as single 1 week shots. So what would come in is what you would do is you would come in, you would have 3 hours to do your lab. You'd get all your data, do all your experiments, take all your data home, have a week to write it up, and then get it marked in the following week. Okay, and then that's the end of the experiment. One of the unfortunate aspects of that is that you only get one shot at the experiment. And if your data is not very good, you go home and try to write that report during the week without getting any chance to sort of come back and get more data or fix things up and so forth. And what this does is it gives you an incentive to sort of start to get into bad behaviors. You know, people sort of drop data because it looks inconvenient, or fudge data to make it look a little better or something like that, hoping that they can get their marks. I've never really liked that way of doing it, simply because one, it gets you in bad habits, and the other is it's just not how science really works. Like if you come down to a research lab, it's not like we do the experiment once and then, you know, send it off to the scientific journal and it's done. What tends to happen is we take the data and we have a look at it and we go, okay, well, this is good, but this bit's not very good. Maybe we need to get better data for this, or improve the equipment, or add a few data points or whatever. Go back down the lab, get some more data, come back, analyze it again, and go, oh, you know, the uncertainty in this bit is too high. Let's improve, refine the method and see if we can get the uncertainty down and get a better result. So we'll go back to the lab and do it again. And then finally, when we're happy that we've actually got a really good, convincing data set where we understand what's going on and we're sort of convinced that it all makes sense, that's when we finally write up the final paper that goes off to the journal that becomes part of the scientific record. So what we've done is redesign the lab program so you get to do a miniature version of that. So what you will do is you'll have 3 lab sessions across the term. The class will be split into 2 cohorts. One cohort will be, you know, have their experiments in weeks 2 onwards. The other one will staggered 1 week behind. And full details of exactly what the lab calendar will be on the Moodle, okay? So don't rely on me for exactly which week these are in. Make sure you have a look at the documentation on the lab part of the Moodle course, because that's the thing that will be right. Anyway, you'll come in, every one of you will be assigned 1 experiment, which is the one that you'll do for the entire term. You'll have a first lab period, and the idea in that first lab period is that you basically sit down and do the experiment and get a data set. And one of the nice aspects of this way of doing it is that you don't have to worry too much about getting the perfect data set, because you get another 2 chances to come back and get more data or fix up aspects of the experiment as you go along. So you'll have that first session, you'll get yourself a first data set, and you'll be expected to do a bit of a preliminary analysis. In the following week, what you will do is have a short meeting with the marker for that lab. So there'll be the same person who marks your report at the end of the term. And the other students in your class who will have done the same experiment, sit down for 45 minutes. And what you'll do is have a discussion about, you know, what data did we get? What did we find? How could we do the experiment better? That sort of thing. This is a chance for the marker to get some feeling for how your experiment's going and give you some feedback on how to improve that so that you produce a good final report at the end of term. You'll then, after that meeting, get another opportunity to come back into the lab, do that experiment again, which doesn't mean you necessarily just do it again, but now you should be coming in with a view of, you know, here's the good bits of my data, here's the worst bits of my data, maybe I need to get more data here. Maybe you've had a really bright idea of how you could extend the experiment, and you can come in and just go, oh, here's a clever thing that I really want to measure, or I want to add more data to my set to make a more convincing thing. After you've done that second session, which will be roughly around week 4, you'll have a week to produce a first draft of a final report. It doesn't have to be fully polished. It's just a first draft that should have all your data in it and a rough workup of it. That will then go out for peer review amongst the students in the course. So each of you will get assigned as a reader on a small number of other students' draft reports. And you'll be expected to do this across around about weeks 5, 6, 7. You'll basically be asked to read them and provide some comments on them. What's good? What could be stronger? What parts of the experiment are unclear? That sort of thing. Try to provide helpful advice. When you get to around week 7 or 8 or so, you'll get those peer review reports back, and you'll have another chance to go to the lab and get more data if you want to. Hopefully those reports and sort of your chance to think in between about what's going on with the experiment will give you some things that you want to do in that final lab session, so that when you finish that final lab session, you have a really good, clean set of data that is nice and convincing and tells a good story, which will be the final story of your final report. Final report will be due around week 8 or so. It will get marked by the same marker that you had the meeting with earlier in the term. And then in the following week, you'll have a short interview with the marker. Ideally, it's about 10 minutes. Maybe it can go to 15. Sometimes it might be a little short. It might be 5, depends whether there's questions or not. I'm aiming at around 10. And that's a chance basically for the marker just to clarify anything that they see in your final report verbally with you, and to ensure that you've got a good understanding of your experiment and can explain it to them. And that will be the end of the course. The final report is length constrained, so it's a maximum of 5 figures and 5,000 words. And so in writing it, what you should be aiming at is at quality over quantity, right? The game is not necessarily to produce like a PhD thesis. The aim is to produce a nice, compelling data set and a good understanding of what's going on, proper error analysis, proper explanations, properly drawn conclusions, that sort of thing coming through in that final report. And so the aim is to get through this process of learning how to take an experiment, do it multiple times, write up a proper report for it. And this sort of sets you up for the third year lab subjects, where you'll do that for sort of part of the assessment as well. Okay. So that's how the lab will work for the term. Full details of it will be on the Moodle site, and there'll probably be a short induction right at the start of term where Tamara will tell you a bit more about how that lab is going to work. Other than that, there's probably not a lot more to talk about as part of this introduction, aside from how to best contact me. So if you want to get access to me during this part of the course, one way is email. Probably the best is adam.mikulich@gmail.com. I like it a little better than the UNSW system, but if you email me at the UNSW system, it will get through to me anyway. Despite my auto forward that warns people it might not, it usually gets through. Probably the other best way to get access to me as part of this course will be via the Moodle forum. So there's a questions on Adam's part of the course forum on the Moodle site that's part of my lecture content in there. I usually check that pretty much every day or two while I'm teaching my half of the course, and pretty much every few days in the other half of the course, just in case anything comes up. And then the other place where I often pop up is on the PHYSOC Discord server. There's a section in there on PHYS2113, and I'm quite happy to float through there and answer questions as people have them come up as well. One thing I will mention, if you contact me by any of those 3 means and the question you ask is a really good one, and it's one that I think everyone's going to have, what I will probably do is take that question and post it as a frequently asked question. I'll make it anonymous who asked it, but post it up and my answer on the Moodle forum site so that everyone can benefit a little bit from the insights that come in there. The other thing that will happen during the term is we will try to get recordings of all of the tutorials and workshop classes. The tutorials should be easy because they'll be using the hybrid setup that we used for PHYS2111, because it will be in the old main building. For the workshop classes, that might be a little trickier. We may have to play with that one on the fly, but at bare minimum, it will be Echo 360. And I'll put those up on the Moodle site as time goes on. So that's pretty much everything I need to cover for this introduction. So I hope you enjoy the course. If you've got any questions, even before the course starts, feel free to send me an email and I'll try to answer them. And if you're having problems as it goes through the course, feel free to get in touch as well. I hope you all enjoy it. I really like the Lagrangians and Hamiltonian sections. It sort of changed when I was an undergraduate myself. It really changed the way that I thought about mechanics. And hopefully it does the same for you. I'll see you in a week or 2.